Hello my dear students, I warmly welcome you to Sia's digital classes. In this lecture, we are going to discuss about one of the important theorem from the second unit. So first of all, see the statement of the theorem. Define inner automorphism of a group capital G. Prove that the set of all inner automorphisms of a group capital G is again a group under composition of a function. Okay, so this is the another new topic, inner automorphism. Inner automorphism, so we have to define the definition. After defining the definition, you have to prove that this inner automorphism again going to satisfy group conditions or again going to make a group. Already it is under a group under the composition of functions. Okay, so first of all, see the definition of the inner automorphism. Inner automorphism induced by A. Here induced by A and in the cyclic groups generated by A is the same meaning. Okay, in the cyclic group we can say that group is generated by A. Okay, without small a that the group does not exist. So here also we can say that inner automorphism induced by A. So you can see the definition. Let capital G be a group. Okay, and small a be one of the element in that group capital G. The function phi of A, okay, or phi suffix A. The function phi suffix A defined by phi suffix of x is equal to ax A inverse. This is the standard equation. Okay, phi suffix A of x is equal to A into x into A inverse for all x belongs to capital G is called inner automorphism. Is called inner automorphism of capital G. This inner automorphism is induced by small a. You can write here A into A inverse. Okay, so induced by small a. So mathematically it is denoted by INN of capital G. So whenever you write this notation INN of G, inner automorphism of capital G. Simple notation, inner automorphism of capital G. So the equation for inner automorphism is nothing but in a group capital G, if you take any element, okay, so the function notation is phi suffix A. Isomorphism we are denoting with phi. Inner automorphism we are denoting with phi suffix A of x. Okay, phi suffix A of x is equal to A into x into A inverse for all small x belongs to capital G. Already small a belongs to capital G. This is the equation. You have to remember this equation. Now with the help of this equation only, so we are going to prove the statement proof of this theorem. So now see the proof. So in this proof, first of all, I am keeping the subheading what we are going to prove. The set of all inner automorphisms of a group capital G is again a group. That is the heading of this theorem. You can also keep heading in this format in the examination. Okay. So now let capital G be a group and small x belongs to capital G be an element in capital G. Okay. Later, now I am taking function representation for inner automorphism. Okay. So phi suffix A be an inner automorphism defined by phi suffix A into x is equal to A into x into A inverse. That is the equation representation for the inner automorphism, that is taken as equation number 1 for all x belongs to capital G. Okay. So now to prove that this phi suffix A of x, now we have to prove that this phi suffix A of x is a group. Okay. So we don't have any deviation from this equation number 1. But to prove equation number 1 satisfies the group condition, here we are going to take the help of the two-step subgroup test theorem that we discussed in the unit 1 only. Two-step subgroup test. By using the theorem, okay, by using the help of the theorem, so we are going to prove that inner automorphism is also satisfies the group condition. So therefore see here, let capital H be a non-empty subset of capital G. I am writing in this format. Capital H is non-empty and it is subset to capital G. Whenever this non-empty subset satisfies the two steps, so that is for A into B belongs to capital H, for all A comma B belongs to capital H. Okay, this condition is called capital H is closed under binary operation multiplication. Okay, capital H is closed under binary operation. And the second condition is A inverse belongs to capital H whenever small a belongs to capital H. This second condition is called capital H is closed by taking inverses. Okay, capital H is closed by multiplication, capital H is closed by taking inverses. These two statements are the statements of the two-step subgroup test theorems, where we proved that whenever these two conditions satisfied, we proved that the non-empty subset, okay, first of all it is a non-empty subset. After proving these two conditions, it will become a subgroup, okay, subgroup of capital G. Therefore, whenever any non-empty subset capital H is going to satisfy these two steps, then it is called capital H is a subgroup of capital G. Mathematically we can denote it is H less than or equal to capital G. Now the same concept we are going to apply inner automorphism. In place of capital H, we are going to take IN of capital G. Okay, in place of capital H, we are going to take inner automorphism. Okay, so by using two-step subgroup test theorem, okay, here the first condition is capital H is closed under the operation, and the second condition is capital H is closed under the taking inverses. Now see here, the set of inner automorphisms of a group capital G, that is simply denoted by INN of G, is a subset of the permutation group S of G. Okay, in the basic definition, capital H is subset or equal to capital G we took. Now here inner automorphism we are taking that. So inner automorphism is non-empty subset for the permutation group. Okay, permutation groups always we can denote with S of N, because these are the symmetric groups. But here permutation group we are denoting especially S of G of a group capital G. Since I into D is equal to pi of small n. Okay, this is the identity notation in the inner automorphism. Okay, I into D is equal to phi suffix e. This belongs to the identity element in inner automorphism. Whenever while in the discussing the introduction of these topics, we can get the clarity the identity element of inner automorphism. So therefore, the identity function I into D is equal to I suffix e is an inner automorphism induced by an element small e. Whenever we are talking about inner automorphism, you have to use the word induced by small e. So therefore, inner automorphism is non-empty. Why? Because identity element is existing in that group. Okay, if at least one element is there, then it is a non-empty set. So therefore, identity element is existing in the inner automorphism. So therefore, inner automorphism is non-empty set. Okay, so after taking that non-empty set, we have to prove that it is a subgroup. To prove that subgroup, now we are going to use two-step subgroup test theorem. Okay, so let I am taking two elements, phi suffix a and phi suffix b belongs to inner automorphism of capital G. Why? Because in the two-step subgroup test, we took a comma b belongs to capital H. Why? Because the elements are existing in capital H are in this format only, a comma b. Why? Because those are integers, natural numbers, whatever it may be. But here inner automorphism, elements are existing in this format only, phi suffix a, phi suffix b belongs to two elements in inner automorphism of capital G. Why? Because it is a non-empty set. You can take at least one element. At least one element means greater than 2. So therefore, now consider I am taking first condition of two-step subgroup test theorem. That is the inner automorphism is closed under the binary operation multiplication. So therefore, phi suffix a into phi suffix b into x is equal to phi suffix a into phi suffix into b. According to the equation number 1, you can write this equation. Phi suffix a will be as it is, and this one is the equation bx b inverse. Again, applying equation number 1, this term will get again, this total term will become one element in terms of x. Now the suffix value is small a. Okay, for this step, if you apply the equation number 1, okay, so a into x into a inverse. In place of a we have a only. In place of x we have this total value bx b inverse. In place of x we have this total value bx b inverse. In place of a inverse, again you can write a inverse. Why? Because pi suffix a is there. Okay, that is. So therefore, after substituting equation, after applying equation number 1, then apply the simplification a into b into x into b inverse into a inverse. From the elementary properties of the group, we discussed that in elementary properties, Sachs and Schuss property. So according to the Sachs and Schuss property, b inverse into a inverse you can write a into b whole inverse. Okay, according to the Sachs and Schuss property, B inverse into A inverse is equal to A into B whole inverse. The remaining two words you can write as it is. So therefore A into B into X, X into, so A into B whole inverse X. Again this term converted into A, X, A inverse only. So that is, you can write what is the place of A into B is there. In place of variable A into B is there. So therefore pi of A into B into X. So if you take multiplication of two elements in inner automorphism, again that multiplication belongs to inner automorphism only. This is the first condition of two-step subgroup test theorem. In two-step subgroup test theorem, we took A comma B belongs to capital H. We proved that their product A into B belongs to also capital H. Here we took the direct product value, then that product value belongs to inner automorphism. This is the first condition of the two-step subgroup test theorem. Now we are taking the second condition. Second condition is nothing but the inner automorphism is closed under taking inverses. Now we are going to take that inverses. So phi of A is the one element and phi of A inverse is the inverse element of phi of A. Okay. So then if you take the inverse property, then according to the property phi of A inverse will be as it is. For this word you can apply the bracket. If you apply the equation number 1, you will get AX A inverse. Here you have phi of A inverse. So then you will get A inverse into X into A inverse whole inverse. A inverse into whole inverse. Okay. Here A is equal to A inverse. Okay. So therefore in place of A, X, A inverse. So you will get in place of A inverse. So A inverse into A into X into A inverse whole inverse. So A inverse into the second term will be as it is. A inverse whole inverse you can write small a only. So therefore after simplifying that step, you can apply the associative property A inverse into A into X into A inverse into A. So according to the inverse property, you will get that value is identity. You will get this value is also identity. So multiplication of identity into something, you will get something only. So that is X. So therefore what is the LHS value? So this one is the LHS value. So therefore pi into A into X. Phi suffix A inverse into phi suffix A into X is equal to X. Okay. It is the first half of the inverse property. A inverse into A into X is equal to small e. Okay. And A into A inverse into is equal to small e. So in this format, so therefore then pi inverse belongs to inner automorphism of capital Z. Now second half, this half part I am taking now. So pi of A into pi inverse of A into X is equal to, again if you apply the condition, equation number 1, for that condition you will get A inverse into X into A inverse whole inverse. If you simplify that value you will get, again here you will get, if you apply the equation number 1, you will get in this format A into A inverse into X into A inverse. So according to the inverse condition you can add those values, again you are getting X. Here X is the identity element in this group. So therefore pi of A into pi of A inverse into X is equal to X. So therefore why? Because the multiplication of two elements, okay, is equal to something value. That element is called identity. Okay. So therefore pi of A inverse also belongs to inner automorphism. So therefore according to the second step of the two-step subgroup test, A belongs to H, then A inverse also belongs to capital H. So therefore according to the two-step subgroup step, the inner automorphism satisfied two conditions of two-step subgroup test theorem. There we call capital H is a subgroup. Here we are calling inner automorphism is a subgroup of the permutation group S suffix G of a group capital G. Symbolic notation, mathematically that subgroup representation we can write in this format. Inner automorphism of capital G is less than or equal to H suffix G, where we wrote H less than or equal to capital G. So we know that after proving that here up to here inner automorphism is a subgroup, but what is asking in the statement, we have to prove it is a group. Okay, but we have by noun theorem trivial statement is, we know that every subgroup is a group itself. According to the subgroup definition, every subgroup is a group itself. So then inner automorphism also subgroup, then according to the noun statement you can also call it as a group also. Therefore the set of all inner automorphism of a group is a group under the composition of the functions. Hence the proof of the theorem. So in this format you have to prove the inner automorphisms of a group. Okay, the set of inner automorphism of a group, again a group under the composition. So in this format, by using the two-step subgroup test theorem, you have to prove in this format. Okay, so I hope you understood this theorem very well. In the next lecture, we are coming with another new topics. Make a perfect practice, whatever you are going to through the practice. So until bye, thank you.